So we're on to chapter 5, and chapter 5 is Introduction to Solutions and Aqueous Reactions. In this chapter, we're going to kind of expand on what we've already talked about, looking at stoichiometry, looking at what's reacting, how it's reacting, but now we're going to focus on things reacting while dissolved in a solution, or some kind of liquid just reacting with some kind of other liquid. But in this case, more specifically, we really are going to look at solutions where we have something dissolved in something else, and that's going to allow it to react. In order to start this chapter, though, we do have to cover some very specific vocabulary to be able to communicate what we really mean. So first, I want to talk about what a solution is and what a mixture is. A solution is defined as a homogeneous, meaning uniform mixture, that contains your solute and your solvent. So solutions, homogeneous, meaning uniform, but your solution is comprised of both the solute and the solvent. I'll talk about what both of those mean in just a sec, but a mixture is made up of two or more components that can vary in proportions, such as a metal alloy or sweetened tea. So a mixture, sweet tea, I don't drink sweet tea, but that's kind of a blasphemy thing to say in Texas. Everyone drinks sweet tea, apparently. But people will put a different amount of sweetener in their tea. And some people just really want unsweet tea, too. I just won't want tea. But if you poll 10 different people, you're probably going to get 10 different answers on the ratio they want of sweet to tea in their mixture. Those are still mixtures. They're still made up of two or more components that can vary in proportions. A metal alloy, same thing. An alloy is made up of multiple metals in a different proportion. And so different metal alloys will have a different proportion of the metals that comprise it. So solution, though, is a homogeneous mixture. So while mixture is just made up of two or more components, a solution is taking mixture and now saying we have a uniform mixture. So, sweet tea, a glass of sweet tea, in theory, it's homogeneous. We probably have the same composition throughout the entire sample. It's still a mixture. It's still a solution. Within that, we've got solvent and solute. The solvent is defined as the solution component in the largest amount. This is usually water. Here's the trick to that. We say it's the component present in the largest amount, but that's not always correct. Sometimes the solvent will actually be present in a smaller amount. It's rare. Most often it is present in a larger amount. But the better question to ask yourself is which species does not change phase? Now, if they're both liquid, say you're mixing two liquids together, if you have two liquids, then the substance that's present in the greater quantity is your solvent. But if you have a liquid and a solid you're mixing, whichever one does not change phase is your solvent. So if you've got a liquid and a solid, the solid dissolves, that solid was not your solvent. The liquid was your solvent. If you have them in the same phase, it's whichever one is in larger amount. The solute is the component in solution that is usually in the smallest amount, and that's why I say the word usually in here, but it is the one that's going to change phase. So the two pictures we have here are sodium chloride and glucose. And so let's make a little diagram for ourselves. Let's say we've got a beaker of water. And into here, we put some sodium chloride. When I put that in solution, it's going to split up into sodium ions and chloride ions. And that's what we see in the picture down here. The picture here shows us, this is the chloride ion being surrounded by water. This is the sodium ions being surrounded by water. It's forming a solution. In this case, the NaCl was our solute, and water was our solvent. Water did not change phase. Water is probably present in a greater amount as well. Let's say we put 40 grams of sodium chloride into 100 milliliters of water. In that case, it's meeting both definitions. We could also have, say, this molecular compound over here. I know the difference here, molecular compound, ionic compound. The ionic compound is broken up into its individual ions, whereas the molecular compound is stayed as an intact unit. Molecular compounds that will do this is like, say, sugar. Glucose, fructose, sucrose, all of those will do it. Let's say I put 150 grams of sucrose into 100 milliliters of water. If all of that sucrose does dissolve, it changes phase. That means that this is your solute. This does not change phase. Which means this is your solvent. So you do have to think about, are they changing phase? If nothing is changing phase, you go for the amount that has the higher amount of it. If something is changing phase, though, the one that changes phase is your solute. And so you need to understand this terminology in order to be able to continue on with this chapter. Some more solution vocabulary: concentrated versus concentrated, dilute, molarity, mass percent, and ppm. So concentration is just a measure of the relative solute to solvent ratio. How much solute do I have dissolved and how much solvent is there? I just want to know how much is in there. Do I have 40 grams of NaCl in every 100 grams of water? Do I have 150 grams of sucrose in 100 grams of water? That's all I want to know. What is the concentration? How much of one species do I have in relation to the other? Concentrated is a relative statement. Concentrated tells us that there is a large amount of solute compared to the solvent present. Large and small here are relative amounts. There are some compounds that do not dissolve well in water. So a tiny, tiny little bit of it dissolving makes this solution concentrated. There are others that can dissolve to no end, like salt dissolves really, really well in water. And so I can dissolve a lot of it before it becomes concentrated. Dilute, there's a small amount of solute compared to solvent. Again, these are relative. I can make one solution. I could then add more of my solute to it, hence making it more concentrated. I could take that original solution I made and mix some of it with more water, hence making the solution more dilute. These are relative to one another and relative to your starting point. We also have molarity. Molarity is your moles of solute per volume of solution in liters, so moles per liter, and we use this as a conversion factor. It must, no exceptions, be moles of solute here to volume of solution, not volume of solvent, volume of solution. The whole solution gets factored in here. Mass percent is the mass of your solute divided the mass of the total solution times 100%. Whenever we see a percent symbol, we always multiply it by 100 to get into percent form. And ppm stands for parts per million. This is milligram of solute to kilogram of solvent. Another way of saying ppm, or parts per million, is you have 1 gram of solvent, or 1 gram of solute dissolved in 1 million grams of solvent. ppm is used in a lot of environmental chemistry. If you probably haven't, I haven't, looked at like the water reports from your city. They send out, I believe it's annual reports are required. They might send them out more often, but they'll send out reports showing like what the different concentrations are of different chemicals in the drinking water in your area. They're going to be reported in ppm. We report that kind of stuff in parts per million just because it's such a small concentration that we want to, the best way to describe it is by talking about it in ppm. Okay, so diagrams and sketches. One thing I really need you guys to do is to start drawing these out on paper so that you can better see this in your mind's eye. The faster you can see in your mind what's actually happening, the easier this class will be for you. And I say that from experience. It took me a really long time to be able to see these in my mind because no one ever told me that. I really liked the guy I took general chemistry from. His name was Dr. Torkelson. He was a sweet old man. Very difficult class. But he never emphasized learning how to see this in my mind. And I think it would have helped me a lot because personally I'm an experimental chemist. I like being able to work in the lab, do things with my hands, and see what's happening. That's how I connect the material. Some students don't work well that way. They don't need to. They can just theoretically push their way through it and they're great. And if that's you, phenomenal. But most students don't learn that way. I really want you working on developing this imaginary picture in your mind so that you can see the atoms and molecules while they're in solution. If you can do this, this is going to help you tremendously in this course. So for an example of what I mean, our symbolic versus macroscopic versus particulate diagram here. Symbolic would be writing copper 2 carbonate. So we know that we split this here. We've got copper, we've got carbonate. Carbonate's 2 minus, so this has to be 2 plus, which means this is called copper 2 carbonate. Or you can call it cupric carbonate. Just a little bit of a review from chapter 3. Excuse me, but this is our symbolic representation. Again, we use elements, formulas, balanced equations to represent our symbolic way of representing what's happening. Macroscopic would be looking at the particles themselves in the beaker. We see here that copper carbonate is this bluish green color. It's kind of a seafoam green if you want to be creative on the coloring here. That's what it looks like to the naked eye. What I need you to see, though, is what it actually looks like when it comes to the particles themselves. When you look at this, I need you to see this in your mind. I need you to see that you've got this alternating positive negative charge. So we've got your copper atoms alternating with your carbonates. Each one has a positive 2 charge, so for every 1 copper 2 plus, there's 1 carbonate ion. This is what's actually existing in this beaker. And this is what I need you to see, and if you can see this, you'll have a better time in this class because you'll be able to see what the atoms are doing when they interact with one another. In order to go to the next part of this video, excuse me, you need to understand this. So if you're kind of struggling with this, pause the video, see if it can kind of try to draw out some of these diagrams and see how they look when you're thinking about the charges. Come to office hours for help, whatever. Read the textbook, whatever you need. But I need you to see this because it's going to make the next part of this video make more sense. So we want to talk about when will a solute dissolve? Well, why is it going to dissolve? There's reasons it dissolves. So what's happening here is we've got 3 different things going on. We've got a solvent-solvent interaction. We've got a solute-solute interaction. And we've got the solvent-solute interaction. And we need to factor or consider all of these when we're doing an example like this and trying to explain what's happening and what's going on. So what do I mean by each one? Well, first, you got to remember the definitions of solvent and solute. You've got to understand what those mean. Remember, solvent is what is usually present in greater quantity, but it's what you've dissolved something in. So the solvent has interactions amongst itself. There's a reason why solids and liquids get created. There's a reason why they hang out together, right? We're going to learn a lot more about these interactions later in the semester, but we need to think about the fact that those solvent-solvent molecules have an interaction with each other. Otherwise, we wouldn't have liquids, we wouldn't have solids. There's no reason they would interact in that form. we also need to think about the solute-solute interaction. How are they interacting with one another? And then we need to think about solvent-solute interactions. So what we have here is, first, formation of attractive forces between your solvent and solute particles releases energy. We focus on this a lot more in Gen Chem 2. So we've got solvent-solvent interactions here that we need to break apart. We've got solute-solute interactions that we also need to break apart. We've got solvent-solute interactions that we want to form. The formation of those particles, the formation of that solvent-solute interaction, will come later on in the semester, early on in Gen Chem 2. But when the solvent-solute interaction comes about, it releases energy. That's the whole reason that something dissolves, to lower the energy. In order to do that, though, we need to provide that the energy that's going to be released by that solute-solvent interaction has to be so much that it overcomes the energy required to break apart the solute-solute interactions and solvent-solvent interactions independently. So if the attractive forces between your solute and solvent are strong enough, the solute will then dissolve. So for solvent-solvent interactions, you must provide enough energy to break up these interactions. These are interactions between different solvent molecules. So when you're thinking about those, I want you to think about questions like, why does water stay together? We're going to talk about this a lot more end of this semester, beginning of next semester, in what we call intermolecular forces that hold these things together. But there is a force holding them together that we have to overcome to be able to form these solutions. In the same sense, you can ask yourself, why do liquids and solids hold together? Now, you may be saying, you're not talking about gases. No, I'm not. We're going to talk about gases in a different chapter, but in gases, we see that the particles pretty much act, not completely, in ideal situations, though the gases act like they don't see any other gas molecules. The molecules are fairly independent in a gas phase. But in liquids and solids, what's holding them in the liquid phase, what's holding them in the gas phase is the energy they have is not strong enough to overcome the interactions holding them into those phases. When they reach the gas phase, it's because they have enough energy to release, to break apart those interactions and float on freely on their own. So for solvent-solvent, these are all things we need to think about when we're looking at solvent-solvent interactions. I need to erase what I've written down, so please pause the video if you need to write stuff down. Again, I apologize. This is why I really missed the whiteboard. The whiteboard always gave me enough room. So for solute-solute interactions, we must provide enough energy to break up those solute-solute interactions. In this section, I want you to ask yourself two questions. Are the compounds ionic? Or molecular? Now, we talked about how truthfully they're probably on a spectrum, and they probably are. But ionic compounds take more energy to break apart because an ionic bond is a stronger bond. It's a stronger attractive force than a molecular compound. Molecular will be easier to break apart. So we need to break apart. Now we've talked about breaking apart our solvent and breaking apart our solute. Now we want to talk about the formation of those solvent-solute interactions. So again, pause if you need to write this down, because I'm going to go ahead and erase it. So the last thing, your solvent-solute interactions. This is the formation of those attractive forces. Between the solvent and the solute. And as stated up here, this releases energy. Generally speaking, enough energy will be released to overcome the solute-solute and solvent-solvent interactions. Does that mean that's 100% the case? No. There are times where stuff will actually dissolve, even though it did not actually have enough energy to overcome that solvent-solvent or solute-solute interactions, or all of them together. And in those cases, we call those reactions endothermic. An excellent example is if we try to dissolve potassium chloride, which is salt substitute. For people who can't have salt in their diet, when you buy salt substitute at the grocery store, that's sodium chloride. Or potassium chloride. Sodium chloride is what we eat as regular table salt. Potassium chloride is salt substitute. When you dissolve potassium chloride in water, if you do it in a glass container, that piece of glass feels cold because it's actually taking heat from the surroundings into the system to help it dissolve. So it can happen, but more often than not, something is going to dissolve because the energy that's involved in the formation of those attractive forces is able to overcome the solvent-solvent and solute-solute interactions. So, dissolution of ionic compounds. Ionic compounds, again, positive, negative charges. We've got a full transfer of electrons here. Water compounds are going to surround the ion and pull it off and away from the ionic crystal. So we talked about how in sodium chloride, we use NaCl to represent table salt. That's not quite correct. This is called the formula unit. And it's the smallest whole number representation that we can use to represent sodium chloride crystals. Sodium chloride exists as a repeating unit of one sodium and one chloride ion, which is what we see in the diagram here. We see these alternating purple and green circles. The purple are your sodium, the positive charge. The chlorine are the green, your negative charge. And we see the chlorine's a little bit bigger than sodium. We know that anions are always larger in size than cations. But what happens here is we see the water molecule. Here's our water molecules coming along. The water molecule comes up and the water orients itself so that in this case, the hydrogens are aiming itself towards the chloride ion. Water has an unequal sharing of electrons. It is a polar covalent compound. The hydrogens have a partial positive charge while the oxygens have a partial negative charge. So those hydrogens, those partial positives of that hydrogen is attracted to that chlorine. Water will come in, surround that chloride ion, and pull it away from the crystal. The chloride is attracted to the crystal because it's hanging out with the sodium that's got a positive charge. But it gains a fan club. It now has 6 waters hanging out with it, all donating positive charge to those hydrogens. It's kind of like, you know what, I like the charge over there better. They're completely surrounding me. And the water molecules surround it and pull that chloride away from the crystal. The same thing happens with the sodiums. Except on the sodium's case, it's the oxygens that orient themselves, because oxygen has, sorry if I'm flipping that so fast, oxygen has that partial negative charge, so the oxygen orients itself around the sodium ions and pulls a sodium ion away from the crystal. And so this happens much faster than any of us can actually comprehend, of course, but this is what's happening to cause these to dissolve. The water molecules are going to surround that ion and pull it off and away from the crystal. So now I have these individual ions floating around. We often describe it as just saying we have Na plus and Cl minus, they're just kind of floating around in solution. That is true. What we don't specify is that they are absolutely surrounded by water. We imply it by the fact that they're dissolved in water. But we have 6 water molecules orienting themselves around that compound. These are not the same as a hydrate. When we talk about hydrates, those waters in a hydrate are captured in that crystal structure in a solid form. This is not the same thing. This is actually letting these ions freely float around. Ions can't be free in a solid phase. They can be free when they're floating around in solution because their charge is being balanced out here by the water counteracting it. So the ion, once surrounded, the ion here, this chloride is pulled away by that water molecule, completely surrounded, and once the ion enters solution, the ion is completely surrounded by the water molecules, isolating it from other ions, so it no longer feels the other ions of the crystal structure. The resulting solution has freely moving charged particles, cations and anions, which are left and able to do things like conduct electricity. This is known as an electrolyte, and we will talk about electrolytes in this chapter as well, but this is how electrolytes work. This is why water can conduct electricity, because we've got free-flowing ions traveling around in the solution. So the ions dissociate in solution. They actually break apart and ionize into 2 different, so if I have sodium chloride, that actually dissolves, or that actually dissociates and ionizes into 2 separate ions. So it is a complete dissociation. Dissociate is the key word there. Dissociation, I call it ionization. That's what's actually happening here for ionic compounds. So, ionic compounds, we often refer to these as salts, dissolve in water. Why salt? We're going to talk about that in this chapter as well, but when an acid and a base react with each other, they form salt and water. The salt is what's left. And we'll talk about that in a different video in this chapter. But ionic compounds, we often call these salts. We'll say like a copper salt, a iron salt, a zinc salt. It means that cation with some anion that's giving it a neutral overall charge so we could have it as a solid in the real world, not just existing in solution. But ionic compound, often called a salt, dissolves in water. This is represented by writing the solid phase as a reactant and the ions that are formed in solution as products. Once dissolved, the physical state of the ions is aqueous, AQ, to indicate that the ions are in fact dissolved in water. We do not include water in this reaction, though, outside of specifying the phases of the ions themselves. So we know it's aqueous. We know it's dissolved in water because we specifically said aqueous here. We're not going to sit here and write NiCl2 solid plus water. There's no need for that. It's implied when we write the aqueous. Make sure your charge is balanced here. So, I've got NiCl2, that's going to split apart. I know chloride is always -1. That means I must have, and I have 2 of them, so I must have nickel 2+. And the other thing to be careful of here is things like a chloride ion, bromide ion, fluoride ion, iodide ion. They are ions present in solution, not diatomics. It's not chlorine or fluorine gas. It's not bromine liquid. It's not iodine solid. They are ions. So it is a single chloride ion in solution. Be very careful and cognizant of this when you're dealing with your diatomics. Okay, what about dissolving molecular compounds? When you dissolve molecular compounds, it is dissolution only because they don't break apart. Sucrose stays sucrose. No ions are actually formed here. No covalent bonds are broken. So C12, H22, O11, solid, just becomes C12, H22, O11, aqueous, meaning dissolved in water. We have not actually broken it down at all. We saw before for the sodium chloride that, let me scroll back real quick, sodium chloride, we see this entire crystal structure that's broken apart, and we get all these little chloride ions floating around. For sugar, though, we see that we've put sugar in, and guess what? We kept it. The whole molecule is kept. Now, they can still be surrounded by water, yes. And we're going to talk about hydrogen bonding and all of that when we talk about solution chemistry later on. So they will still break up into the individual molecules. The molecule itself will no longer stay associated with another sugar molecule, but we're not going to break up the sugar itself. We're not going to break up the molecular compounds themselves. Whereas sodium chloride broke up into Na plus and Cl minus ions, sugar stays, or any molecular compound stays as the molecule. We've just broken multiple molecules away from each other.